Okay, I think my strategy for this week is today I want to lecture on chapter 3 from the textbook, and I played around with the slide formats a little bit, so we'll return a little bit to the ugly slides. But what I'm going to try to do is intersperse some like interactive questions throughout so that we can break into a dialogue every so often. So it's a little bit more interactive. I'm gonna see how that approach kind of fits the mold for this class. And then what I might do for Thursday is actually a sample workshop of what to expect in terms of how to present a technology. So likely what I'll do is I'll kind of do a 1 hour and 15-minute workshop on something likely like Python or a Python application so that everyone gets a good understanding of what the Pythonic syntax is. So I think that's going to be my goals for this week, leading into next week, where hopefully we can then start doing the tech workshop series all the way until we've covered all the technologies we'll have to cover. So with that said, the reason why I want to cover chapter 3, though, is if we look at the textbook is broken into 4 primary parts. And so the first 3 parts are chapters 1 through 3 that kind of discusses and defines what is software engineering. So by the time we get through this chapter, you should have a very solid understanding of what it means to engage in software engineering. You'll see there's a lot of like overlapping concepts between chapters 1, 2, and 3 if you've already had a chance to read them. And if not, this will be a good overview of them. I find that when I make these slides, it's a really well-crafted book that just even begs to have even more examples crammed into there. So I'm trying to give you a little bit of supplemental content that's not included in the textbook itself in terms of some case studies or defining case studies a little bit more so than that are kind of alleged to in the book. And the second part is about optimize for learning, which we have discussed already about what it means to be a software engineer. And then next, optimize for manage complexity. And then finally, the final part is going to be the tools to support engineering and software. And you're going to be covering a lot of those tools. So we won't really need the textbook for that so much. And so here, after today, I'd like to be done the first part of the textbook. Just out of curiosity, has anyone started reading the textbook? Just what are the general impressions from those of you who had started reading it?
I think it makes perfect sense because now you have a strategy. You just don't have to guess that something works. You can keep testing and getting feedback and not know where you are going to go, but let your feedback shape where you.
Yeah, that's exactly right. I think one of the biggest values of this textbook is there's a lot of pearls of wisdom, right? So you have a senior level developer who's read all of the traditional academic works related to software engineering and then went ahead and modernized it for today's more modern team collaborative approach and kind of really hammers in what works and what should probably be avoided if your goal is to deliver on software. And so that's why the first couple of chapters really try to hammer out and define what is software engineering. We're going to finish that up now. Okay. So this chapter is going to be called The Fundamentals of an Engineering Approach. And so as we've already stated, there are a variety of engineering domains. We've specified many of them in the last couple of lectures, and they all have their own unique methods and challenges. But despite all of their kind of the unique considerations that they have for whatever it is that they're constructing or building or solving, there's some general engineering principles, some foundational principles that they all have to adhere to. And again, we're going to lean into that for defining software engineering. So the common principles that we've laid out, and we're going to stick to this, is scientific rationalism. This is where we're grounded in scientific principles and reasoning. This is where we rely on logical analysis and evidence-based decision-making. And then the second is pragmatic and empirical. So here we're talking about practices are actually practical and focused on actually delivering real-world applications. So we're not just existed in a theoretical space like maybe math is allowed to do. We actually have to deliver something that works. And so when we talk about that, we can lean into empirical methods such as experimentation and observation so that we can go ahead and make progress towards whatever our end goal is. So how do we apply those foundational engineering principles to software engineering? How are these relevant? Well, software engineering, just like our other engineering disciplines, would use the scientific rationalism and empirical methods in the approaches and methodologies we define. So when we talk about test-driven development, that's effectively using empiricism. And when we talk about these agile methodologies, this is this kind of iterative development where we're getting feedback and learning and experimenting and learning and experimenting. So building on that foundation, what's the point of software engineering? When we go ahead and deliver our software, it's not just to deliver the product. We already talked about that. It's not just the code base. There's goals in mind. Like when you build a bridge, you just don't want to build the bridge and say the bridge is done, and then you don't care if it stands the next day, right? Longevity is part of the planning. It's part of the implementation. The maintenance of it is all a fabric of the engineering process. And so we're going to, again, lean into that. And we want to keep in mind that we want to adopt methodologies and approaches that will make our job in maintaining the code base easier. This can make the workload of actually implementing it a little bit harder, but the payoff is that later on when you have to change it or mutate it or update it, it'll be easier. You have a plan for that. And again, we have already discussed some of these. We'll reflect back on them. We can make use of things like modularity, abstraction, the design patterns to be able to go ahead and give us that longevity that we need. But at the same time, we also want to create a solid framework, something that we can build off and expand in the future with other projects. We want to separate it from that of a craft where we're having to rebuild everything from scratch each time. Okay, so here now I'll pose to you a question then. Do you have any examples of your experiences where you've used either empirical methods or scientific approaches to go ahead and improve on a software project that you've worked on? So we've talked about what it means to take an engineering approach. You might not consider yourself a software engineer now, but have you at least done like pseudo engineering things? Can you at least identify an engineering-like practice towards building a homework solution or developing a project?
For projects once, I go like a little later that I like, and I had like 10 to 15 test sentences that I would try to run for each iteration on it to see how it changed.
Yeah.
If I like this.
That's exactly what I'm talking. So you test out, you created these test cases, and then you kept evaluating the state of your application until it satisfied what your requirements were. And that's effectively engineering put in practice. And I'm assuming that's probably what you all have done at some point. I don't imagine many of you have like sat and just like coded without ever compiling and just testing at some point to make sure that your code base runs. Like how often? Now, I see that a lot in Java 1, right? Like in Java 1, you might be like, oh, I got to do this homework assignment. I'm going to build this MUD. I'm going to start coding it. You're like 500 lines in. You're like, let me see if I can compile. And then you have like the dreaded 3,000 errors. And then like you find you missed a colon, and then you get to like 200 errors, and then you fix something else, and then it's 300 again. And you're just like, where is all the bugs on this? And that's probably where you started to learn, oh, let me just do a little piece at a time and start to compile in between and just make sure that stages of it are working. But the goal here is to illustrate you already do an engineering-like methodology. We just want to harden that. We want to focus in on that, and we want to be more intentional about that. Okay, so one of the things about software engineering, just the software landscape, is that it's malleable. It evolves really quickly. It's ever changing. It's like a big ripply like ocean. And so this is an industry of change. There's no like stepping away from that. You've seen that probably since you started your career as a student, and how many technologies have changed, even just the versions of the language you've been using. I mean, Java at this point has 2 new versions each year. Every 6 months, there's a new version of Java that comes out. JavaScript gets updated way quicker than that. Okay, so what does this mean? Well, whenever you are in a landscape that has changed, there's risk involved. However, and we're going to see this, you have risk for evolving, but you also have risk for not evolving. And then the decision is, should you evolve or should you not evolve? Or if you should evolve, how should you evolve? How do you measure those things? Let's talk about that for a little bit. Okay, let's start with the risk of evolving and just understanding change in software development. So the software industry is characterized by rapid changes and excitement over new technologies. Like that's one awesome thing. You'll see like lots of blog posts, YouTubers, release documents. You can be part of still like these email chains about all the updates for various languages, frameworks, tooling, ecosystem developments, like game engines, like you name it. If it's technology based, one of the like defining characteristics of technology, especially digital technology right now, is it's rapidly progressing and becoming better and better because you have so many involved people who have their hands in it. And so you get to be a part of that ecosystem. You get to be a part of that community who's pushing this ball forward. But with that said, there's a lot to learn and a lot to make decisions on. So despite the hype, many of the changes actually have minimal impact on the core principles of software development and can sometimes actually lead to inefficiencies and complications. I stated earlier, Java sees 2 major revisions a year. Does it really affect an application you design if you're not on the newest version of Java? Probably not. It's not going to be that impactful. So what is impactful? Let's kind of start to do an autopsy. Let's kind of delve into that. So first of all, let's talk about the risk of change, like I said earlier. What could be problems if we were to be those eager beavers and constantly try to adopt the newest technology that gets released day after day after day? Well, you're probably going to run into many of these problems. One of them could be overcomplication. New technologies can actually increase the complexity if they're not a good fit for the project. We're actually going to look at a case study where that's given in the book and kind of elaborate on it, where this actually has happened. And we'll do a compare contrast. You can have performance issues. Tools, especially if they're newer tools, can cause bottlenecks if they're not optimized for your specific use case. There could be a learning curve for all the new technology. So if you know how to do something already, but there's a newer approach, you have to learn the newer approach, the newer tool. And that comes with a technical debt, because now you have to learn the new thing before you can start building things with it. Newer technologies typically have poor support, poor documentation. The API might be incomplete. The documentation might be not all there. It might not have a big community of other developers that you can rely on getting answers from. You might have to look at more source code to understand what's happening with the tool, or just explore the tool more. Again, more technical debt. Limited expertise. So again, you have less team members who you can rely on to give you that domain expertise if you have a quick question. So if you did have a domain expert who could give you an answer in 30 seconds, you might end up taking 3 hours trying to figure it out without that domain expert. And lack of stability. New technologies aren't guaranteed to last long, right? They haven't proven to be like stable releases. There have certainly been instances, say for instance, and I think I give some examples on the next slide, like for instance, Meteor, was branded as, has anyone heard of Meteor before? Like that just shows you how dead it was. Just like 5 years ago, Meteor was a super popular buzzword for a one-stop solution for building web applications. It managed your front end, it managed your back end, it managed your database, it managed all the connections in between. It was completely in JavaScript. But guess what? That made for a very brittle system and an ecosystem where you have front ends that are spinning out of control and evolving, and you have back ends that are doing the same. You can't have one developer trying to keep up pace with all these other developers and not lag behind. And of course, that's what happened to Meteor. But if you had invested in Meteor, if you were a Meteor web shop, now you've hitched your wagon to a technology that is defunct. And so now you're going to burn yourself with a lot of technical debt, having to invest in a whole nother updated technology to convert over, or you're just going to have to depend on that legacy software, whatever the last iteration of Meteor is, and just hope that that's going to produce a stable, scalable build for you until, well, I guess it doesn't. The point is, there is a risk of evolving. This is something you have to make a decision on. This is something you have to consider deeply. It's not just when there's a trend in the industry, you should jump on it. Doesn't mean you should avoid the trends either. We're going to look at the risk for not changing. Oh, here, I have a discussion problem, trying to make this more interactive. Can you think of any examples where adopting a trendy technology or methodology led to more harm than good? And how does it affect the project? And what would you have done differently, or what could have been done differently?
So I worked a lot with Python, and I was always trying to use the newest Python version, and that led to many problems with some packages not supporting the newest version, and I was debugging, and I couldn't tell what's not working. And then I just one time installed another Python version, and it worked like that.
That is such a great example, because I have the exact same experience as you. Working in Python, you're like, oh, the new version of Python has these really cool operators that allow me to work on sets. And, you know, I'm not working on sets. This isn't a problem. I just like the idea that I could potentially work on sets. But guess what? All of a sudden, NumPy doesn't work on the new version of Python. And I do depend on NumPy. And I try to run my code. I'm like, oh, no, I can't import my code because it doesn't work on this version of Python. Then I have to step back for a code base that actually supports all my dependencies. What was your observation? Theranos?
Elizabeth found the lady who had this blood testers, but it was like really buggy and it gave false results and she faked everything.
Oh no. Oh, that's unfortunately another thing that happens is, like, when you are in an industry fed with hype, you can get charlatans too. And they're going to sell you a bill of goods. And like, even if the software packages or APIs or the SDKs or whatever you're working in environment-wise is free, it's not free if you're investing a lot of time and effort trying to build into it. That costs you time. And your time is probably more valuable than, even like, once you get into the industry, more than a couple of $100 or $1,000 for a license on something, for sure. Yeah, some very interesting examples.
Not like necessarily like software. Well, I guess it is, but switching to how much work.
Oh my God. Well, there's a special slide that I saved for Workday. Let's reserve that. We'll cover Workday in this slide deck. Okay, so let's talk about the case study that the book does. So, and this is one that is kind of relevant to you in a way, because it's for Java developers in particular. And so here, let's set up the narrative. First of all, the case study it's a comparison between Hibernate versus SQL. Has many of y'all taken databases already? So you're already familiar with what SQL is and what the role and responsibility of SQL. Has anyone worked with Hibernate before? So Hibernate It's very popular with being able to build Java-based web solutions like back-end servers to be able to go ahead and connect to your database as well. So there are two different database solutions. Let me set up the scene now. So imagine that you're a Java developer. Shouldn't be hard to imagine this because that's probably what you primarily are comfortable using. Because is databases in Java? Yeah, okay. Okay, so imagine you are a Java developer working on a project that requires frequent and complex interactions with the database. Your team is excited about adopting a new technology and has decided to use Hibernate. So instead of just using pure SQL, you would use Hibernate. I'm really familiar with Hibernate, the fact that our old web application class that used Spring Boot would use Hibernate to go ahead and interface with the database, because that's a technology that GE Digital used to use. So this case study really reminds me of some of the difficulties students had working with Hibernate. Anyway, so it's a popular object relational mapping and ORM library. And of course, the idea here, the reason why you would use this and not just SQL is the belief it will streamline your database operations and improve productivity. So at first glance, Hibernate seems very promising because it abstracts the underlying SQL queries, allowing developers to interact with the database using Java objects. So it allows you to start thinking of your database in terms of Java objects. One reason why JavaScript is so popular on the back end and the front end is it allows the same kind of metaphor of data and logic management of your code on both the front and the end, and even in the database. You can use Mongo, which effectively lets you use Java JSON or JavaScript objects to be able to store right from your server into the database or extract from your database and populate right back into your server and then put right into your front end. So this idea of having a similar model of data between when you're effectively serializing it to store it or extracting it so that you can actually use it in your application seems like a real blessing. It's like, oh, great, this is great. I don't have to pull these data entries out of my database and then build them into objects, right? Hibernate takes care of that for me. This abstraction layer is supposed to make database interactions easier and more intuitive, aligning well with object-oriented nature of Java. However, as the project progresses, the team begins to notice some unexpected challenges. And so Kristen Gorman, a software developer and speaker, highlights these challenges in her presentation comparing Hibernate with direct SQL for database interactions. And so what her team had discovered is that, well, first, while using Hibernate, there was a complexity and code volume problem over just using basic SQL. Here, initially, the promise of Hibernate was to reduce the amount of boilerplate code by automatically generating SQL queries. However, in practice, the team found themselves writing more code in order to configure Hibernate and manage its entity mappings and handle its exceptions. So, for example, just doing simple CRUD operations, and if you don't know what a CRUD operation, that's your create, read, update, delete operations. Those are your core operations that you can do in a database. That could have been performed with just a straightforward SQL statement, now requires understanding and managing all the Hibernate specific configurations, and it introduced a new concept, if you haven't seen it before in Java, annotations, where you have to then populate all sorts of annotations inside your Java code, which the framework then parses and then does a build off of those annotations for you. So again, another steep learning curve on how to get all this into the workflow. And then it wasn't just the complexity and code volume that Hibernate added to their project. It was performance and understandability. So the team also started to notice performance issues. Hibernate's abstraction layer actually introduced additional overhead. You had to build more Java objects. And with that, you had to import more dependencies. And I don't know if you've ever built or deployed a large-scale Java application, but you can really get into a dependency hell with that. And so this would actually result in slower query executions compared to if you just stuck with direct SQL. Also, debugging became more challenging because whenever something went wrong, you had to look at the generated SQL. You couldn't look at the SQL you authored. You had to see what Hibernate did and see, well, why isn't hibernating connecting with my database the way I expected to? Again, that's going to create more technical debt for you. Now your developers spending more time debugging the issues between frameworks as opposed to just going ahead and doing the logic, being able to code the logic directly into SQL. So this is just an illustration where you have a promising technology, and it was, I saw it rapidly adopted 5 years ago when it was in its peak popularity. And did you learn Hibernate in databases? There's a reason why. Anyway, so we already talked about the findings and the reflections here. Kristen Gorman's insights reveal a critical lesson. Adopting new technologies or methodologies doesn't always lead to better outcomes. You know, in the case of Hibernate, the initial appeal of abstraction and automation was overshadowed by the increased complexity, reduced performance, and difficulty in debugging. The team reflected on this experience, realized that it caused them to slow down, but then you're allowed to pivot. Then after a little bit of incremental development and a realization that it wasn't working, they could pivot and readopt a technology that worked better for the team. This is what it means to be able to learn and be adaptable. It doesn't mean you shouldn't try out new technologies, but try them, test them in a limited fashion before you 100% commit to deploy your entire application in that environment and see how well it grows out for your needs. Okay. So let's talk a little bit. We're still on this impact of change, examining the impact of change, because this is a real consideration. This is going to be something that you're going to be faced with throughout the entirety of your career. So there's a temporary nature of change. This is where you have short-lived trends. And so here, yeah, this is going to be examples of hype-driven technology. I try to list a lot of the JavaScript ones in here. So the software development industry is often influenced by buzzworthy trends and technologies. I don't know if you've noticed that before, but you get buzzwords all the time that just get thrown out. So there was a show a number of years ago now called Silicon Valley that I think was on HBO. They did a great job of kind of poking fun at how like buzzwordy the kind of tech industry can get at times. And kind of how petty sometimes the arguments can be too, like whether it's Vim or Emac or tabs versus spaces. And also the lack of lasting impact. So you do have these frameworks that might surge in popularity and then just fall right off the cliff. And I've seen both those happen a number of times, just while even teaching classes, like adopting technologies in the classroom, and then a couple of years later, adopting new technologies in the classroom, because the ones that were like the ones to learn, the ones that the hiring managers are saying, we want your students to know, suddenly change to something else. But this is why software engineering isn't just learning what a tool or framework is. This is one of the big dangers that a lot of the boot camps have. Boot camps don't really teach you how to code in an abstract sense. They don't teach you the design patterns to necessarily succeed in an ecosystem that's going to change over time. It produces really good cogs in a machine that's using a very particular set of tools for that time. So a lot of emphasis, if you've ever been to a boot camp, is to learn a specific set of technologies to build a particular type of application. You take this like really narrow path, but you don't know how to wiggle out of it. So if you have any problem that falls outside of this very rigid set of circumstances that's covered inside the boot camp, you're going to get lost. I don't know if you've interfaced with anyone, either in an internship or whatnot, who have gone through a boot camp and just kind of had a dialogue and just see how the experiences are slightly different. Not to belittle boot camps, they have their place. I'm just saying that usually the methodology leads to a more brittle knowledge, knowledge that can break down much quicker, much more rapidly. And that's not what you want if you're going to be in a domain where the tools are changing so quickly. Okay, so let's talk about some examples of this kind of imperial changes. So we have these hype-driven technologies. So consider the rise and fall of, say, for instance, just some certain JavaScript frameworks. I talked about Meteor. Does anyone remember Backbone? Backbone was like the back-end JavaScript before Node was a thing. Has anyone heard of Dino? That's also a back-end JavaScript that's made by the person who made Node. Doesn't matter, right? Not really used. Angular. This might be pretty contentious. React has certainly surpassed and supplanted Angular, but Angular was at the very forefront before React rolled out. Cordova. Cold Fusion. Bower. Before NPM became super popular, you used Bower as your build tool. So just examples of these technologies that really popular and then just fall off because some newer technology comes out and replaces it. Bootstrap for responsive styling. And then you have, besides these hype-driven technologies, which kind of are like, they explode and you'll see like all these stories, these news feeds on it, talking about how this is going to be the technology of the future. And sometimes it is, right? Like React has actually stood the test of time. It was promoted just like all these other frameworks were, but it's been able to kind of mature into what it is now. And you can actually take, I think, at least 2 classes that deal with React inside this curriculum, one in web apps and the other in mobile apps. But also you have methodology fads, because keep in mind, we're going to highlight this again in these slides, is that, also let me do this. Okay, it's not just about using digital tools to build your code bases out, but it's about getting people together who are using the digital tools to build code, right? This isn't a solo activity. And so you have methodology fads as well. So we're going to talk a lot about agile-like methodologies, but there's a lot of methodologies that are agile-like that aren't, that kind of borrow, but kind of break down because they're not delivering the same thing that a good agile environment will. And so you'll see some of these like really popular trends in programming. Say, for instance, does anyone remember extreme programming? That was like a fad of a methodology fad of how to bring people together to go ahead and produce software. Worth Googling if you haven't seen what extreme programming is. And it still has semblances that are effective and useful. Okay. Here, I feel like I've said enough. I feel like now time to give you a prompt, a discussion prompt. Okay, so let's compare and contrast software engineering with, or at least the software environment. So I've talked about how malleable it is, how much it can change. So I want to contrast it with other industries. I'm a big fan of analogs, trying to see, well, what is like software engineering, but what's different? Because that can give me a different vantage point. It can give me a different view of the field I'm trying to talk about. Let's compare software industry to that of food science. When y'all were in school, remind me, I gotta get in my mind how old this goes. Do you remember the food pyramid?
Yeah.
Okay, perfect. So imagine old frameworks and technologies like the food science industry. I guess that's an industry, right? The food science domain would promote the importance of the food pyramid, right? Like that, I feel like that's not only just not right, but downright bad advice. Now, in today's understanding of food science, And so here we've seen a significant shift in recommendations over the years. For example, the food pyramid was once widely advocated as a standard for a healthy diet, but is now considered outdated and even potentially harmful in some aspects. So what parallels do you see between this trend, the food sciences, and so just seeding that? I want to see what kind of correlations can you draw from that? And there's other things too. You don't have to stick to food sciences. Think of other things that might be like education or fitness or business practices, things that are kind of like the software industry, where there's an evolving set of methodologies, practices, and tools, and that some fall out of favor for whatever reason, and then new ones get adopted.
Pretty extreme, but.
Oh, and so you said when they started to put.
But yeah, that one specific applied to gasoline. Oh, no, I couldn't.
Do you remember they started putting corn in gasoline too? Ethanol? Yeah. Yeah, you're right. Like when I go to Taco Bell, just right on Elysian Field, I interface with the computer, and the number of times that I get wrong tacos now has dramatically decreased because I can communicate with the machine much more effectively, exactly the custom order I want. They get to render it on their side and build it as per expected. I remember calling out at that little speaker number of times and sometimes not even getting a taco. It'd be like a burrito or something. Okay, so there's a value of just seeing how this isn't a unique issue in software engineering. We could see this has happened in other domains. And when I was trying to reflect on this, I really thought strongly of food science, because it seems like there's always a food fad, right? Like a fad diet, like we have a fad technology that's going to solve your problem, whatever your dietary problem is. And then it's just going to be usurped or proved wrong, or, if you're on that diet, it's not going to work and you're going to have to find another, and you invested all this time or money or training or whatnot, right? Or it could be like exercise. Like I remember when jazzercise was a thing, and that's right. I'm going to do this agile approach and try to notice I'm keep playing around with my slides to find out how I can best get them to fit. Like I liked when we had stops and pauses and I could ask you. So I'm like, well, when I make my slides, let me find where I could put pauses where I stop talking and remind myself to stop talking and remind myself what kind of question I can ask you. And that gives us a better back and forth. You're going to be, if you're more engaged inside of, if we create a dialogue and you're more engaged, you're more prone to remember the things I'm saying because you're invested in it. I'm just not talking at you. I'm talking alongside you. That's a great realization. Okay. So we talked about how we have this impact of change and how we can actually map it to these other things. That's going to bring me to another realization about, well, what does it mean? Is there a ground truth to software engineering? And so I guess that would be like saying, is there a ground truth to food science? Is there a ground truth to medicine? Does it work that way? There's a reason why medicine is called a practice, right? And so if ground truth, so the question is there such a thing as ground truth in software development, or is it more about adapting to the current understanding and context? And then how does it compare to fields like food science or medicine when recommendations evolve based off of new research and the understanding of how things work? So when we go back to that idea of discovery and learning of how our playing field works, because very much in the real world, that's how pharmaceutical and the medical field is. When you're talking about when you're talking about organic chemistry and the way that molecular proteins can kind of bind or twist or respond to whatever the medications that the pharmaceuticals are developing, whatever proteins that they go ahead and administer, that's not something that's easy to witness, right? You got to actually create these physical substances and then test and train, and you can't see how it's being denatured. You can't see how it's being manipulated in three-dimensional space. There's all this computational biology that's involved that Dr. Suma can say way better than I can because that's his actual specialization. But there's a reason why there's so much synthesis and there's so much kind of practice in that. There's a lot of experimentation and then new context that's brought in to understand how things can work better, and then you update. That's what science is. Okay, now we're getting into the slides that are going to be more relevant to Workday. So you've probably heard a lot about the attempt to make 10x gains by adopting new technologies, right? So why should I do this? So it's going to make you 10 times more efficient. Have you heard that before? This tool will make you like on a factor of 10 quicker or more robust or more efficient or more streamlined. Well, what we actually end up seeing, it's more like the opposite. Usually poor decisions and poor planning or outdated practices result in 10x losses. It's more likely to have 10x losses than 10x gains. Not to say you can't have it, but let's just say if this were a casino, the house usually wins. Okay, let's talk about some examples of what can lead to 10x losses. Sticking with outdated practices or processes. Why? Well, companies that continue to use outdated development processes, let's say the waterfall model, because that's one we've already talked about, and you can already visualize what the deficiencies of such a model is. That may cause that team to struggle to adapt to changing requirements and fail to actually deliver the software either on time or at all. Let's talk about other things, though, not the waterfall model. Let's talk about, say, for instance, if you had a company, a firm that just wished to outsource the development to some low quality standards that are outside of their industry. So instead of having in-house developers, they're just going to hire a contractor to do it. Well, what could be the potential pitfalls of that? Well, companies that outsource development could potentially give work to teams with lower quality standards than what they would have maintained in-house, or have insufficient expertise because they're not actually in control of hiring the developers. They're just giving their requirements to the other team who's going to be in charge of hiring the developer and whatever their standards are. So if they're bargaining based off of like a fire rate deal, you might get very inexperienced developers. So what's the consequence of that? Well, that can lead to immense technical debt. You might get a code base that is not scalable, that's not well crafted, that has to be completely refactored.
Just an overall question, because what's confusing to me is that people follow the waterfall model or whatever model in the day, thinking or proving to themselves supposedly that this is the way. How did they get that wrong? And how do we know this way we're not?
Well, so it's just like food science. It's not so much that they thought to themselves that this was the wrong way. The waterfall model was adopted from traditional engineering standards. So when software engineering was kind of emerging and it was on the shoulders of like electrical engineering as well, it was clear that engineering managers who were well practiced and taught in managing engineering projects. So like deciding what are all the requirements and then developing a plan to meet all those requirements and then designing a system that met that plan and then implementing that system and then testing and validating that system and then maintaining that system. That's still the thing you're going to want to do if you're going to build a bridge, right? Like you want to know exactly everything that's going to happen before you start laying down any foundation.
So it was because computer science was so closely coupled with engineering back in the day, the hardware.
Exactly.
Why?
There wasn't a good distinction between the electrical engineering and the computer engineering. In fact, computer engineering didn't really have a known set of principles that worked. So they were having to use the context of what they knew. Just like with food science. At one time, we thought it was a good idea to have a food pyramid. But the more we learned over the years, the more we got to see the results of using the food pyramid in practice, the more context it gave us, the more we could adapt and readapt to find methodologies that work better. And so for the same reasons that food science evolved, that's the same reason software engineering practices and methodologies evolved. Oh, and then a current one you might see, the use of AI tools that might produce erroneous output. I don't know if you've encountered this, but have you ever tried to get, say, for instance, maybe ChatGPT or Gemini or one of these other tools to produce code for you, and then it didn't work quite the way you needed to, and then you spent more time trying to debug this erroneous code that the AI generated for you than if you just sat down and built it from scratch with your own kind of planning. And so that's technical debt as well. There might be the expectation, oh, I can save a lot of time by just using an AI generator to produce all the code and then just kind of wire this together. And in practice, that hasn't been the case. You need to have a strong kind of managing developer that can look over the generated code and ensure that it works the way it's expected to work. And it doesn't. If you have junior developers who are just generating code and trusting that it works, that can lead to huge security vulnerabilities. And then that has a cost too. If you lose people's personal data, there's a financial cost to that. Okay. Okay, so there's also talking about the impact of change. There's something that can hide poor choices in software methodologies or tooling, and that could be hardware. We already talked about how improved hardware actually led to having the ability to have more complex software, where we then realize, oh, wait, building software isn't so easy. We can't just always throw like better hardware at it. That doesn't always solve the problem. But sometimes it can hide that problem. Like, for instance, if I wanted to play the game Diablo in 1996, I would have had to have a high-performant computer in 1996. Now I think it runs in the browser. I think it's actually been compiled for WASM, WebAssembly, so you can just open it up in like Google Chrome. Like you can run, so hardware can run quick enough as to hide software problems. But let me try to motivate how they should be tethered together. And so I'm going to use as a motivation actually a company that likes to package their software along with their hardware. Let's talk about the Apple iPad. I have an Apple iPad, but this is definitely worth kind of picking apart. So the role of hardware advancement. Every year, Apple announces a new iPad, right? Every year, almost by the calendar date. And each year, it gets a more powerful processor, it gets increased memory, it gets enhanced graphics, right? At this point, there's what? Is it the M3 chips inside the iPad now? They have the same chips as their MacBook Pros now. So these upgrades allow the iPad to perform complex tasks like video editing, gaming, or showcasing its hardware potential. But progress here is masked by hardware improvements. Despite the powerful nature, the iPad's operating system, iPad OS, which is a derivative of iOS, not Mac OS, often limits its capabilities. It's got restrictions on multitasking, and the file system access prevents professional grade apps from really utilizing the hardware that's built into the system. So here, this creates a misleading sense of progress where the hardware suggests that the iPad can actually replace your laptop. Has anyone ever tried to use an iPad as a laptop replacement?
Used to a lot for like baking and like production and whatnot. They replace it to a certain extent.
Yeah.
It's just so-
And then it just gets cumbersome.
It's so-
It gets cumbersome because there's so many things you want to be able to do in a Mac-like environment that you're just limited because of the software ecosystem. So here, the software is actually, you have this really powerful hardware comparable to a MacBook, but in its actual use case, it's a consumption device, it's not a production device. And the moment you try to use it as a production device, it falls apart very quickly, except for these really niche categories. So here, true progress in software methodologies, the real progress requires more than hardware upgrades. It needs software advancements that fully leverage the hardware. Because wouldn't that be ideal? Okay, so we've talked a lot about what is not good change, right? What is not transformative change? Let's talk about what is transformative change. And we've already mentioned this before, like how can we actually make software better? How can software engineering actually improve the state of, well, software engineering? Well, we usually see that when there's a transformed approach to software development. So when we move from assembly to C and introduce a higher level programming concept, we saw much more complex applications being built. Those applications were much more robust. They were much more likely to succeed in development from the planning phase and be as fully featured and meet the requirements that they needed to be. That's how we're defining success. The transition from procedural to object-oriented programming. Again, another example of this. The shifts in programming paradigms have more significant impact than changes between individual languages. Like changing between Python and JavaScript is trivial. You can do the same thing. It's the paradigm shifts of how you can organize your code and deliver it, which really matters. And I could do object-oriented programming in either of those languages. I could do functional programming in either of those languages. I do procedural programming in either of those languages. Okay, let's talk about the risk of not evolving and the challenges in learning and unlearning. So we talked a lot about why you should be careful when you evolve or change. Let's talk about what happens if you decide to stand still and just keep the status quo and just kind of plug your ears up and say, this works, we're not going to do anything about it. Well, the software industry often struggles to transition from outdated methodologies to newer, more effective practices. You see this all the time where you have a shop that has legacy software that they're looking for. Let's say, for instance, what's a good one? Like, for instance, the NRL still needs like Fortran developers. And so sometimes there's some government agencies that still need that's a perfect one, COBOL. And it's because all of these systems have been engineered and they don't want to invest in having to update them. But there's a risk in a resistance to change. Here you can get stagnation and technical debt, right? Because now you're having to support software that's not really supported any longer. And the expertise is not very readily available inside the marketplace. And if you have to expand, or if you have to scale it out, or if you have to add new features, that might be even impossible to do.
I did hear that they get paid.
Well, of course, because there's not as much competition. Yeah, there's not as much competition. But also, your marketplace is going to be very small too. Missed opportunities. So holding on to outdated processes can delay product delivery, miss market opportunities, and prevent staying competitive. And you might lose that competitive edge. You might have actually been the dominant player in that marketplace, but if you sat on your laurels, you might lose it. And in fact, can you think of an example where there was whether it's an IT company or another type of company that was resistant to change, and it was their failure?
What?
Ah, that's a good one. That's actually the one that I put on there. Yeah, Blockbuster seems like the very obvious example here. Very resistant to change, stuck to that brick and mortar shop, made a lot of their income based off of late fees. You remember having the late, you'd have to pay the rental, and if you didn't get back like 24, 48 hours, you'd then be hit with a late fee, which was like 2 times the cost of the movie rental itself. Sometimes it was cost of the movie.
They closed down a while ahead.
And what's funny is that Netflix actually approached Blockbuster when they were the market leader to try to coordinate and partner with them to start doing like DVD mail-in rentals and being able to go ahead and start trying to facilitate a streaming service. They always wanted to do the streaming service, but streaming, the internet connections weren't quick enough. So they did a DVD rental until high-speed internet was more widely adopted, and then very quickly pivoted to streaming services. And now look at where this is at. Blockbuster is no longer a thing. Netflix is not only like the market leader in video delivery, but just content creation too. Like they're just driving that entire kind of entertainment sector. Okay, so I guess let's just talk about some of these takeaways. Not all change is progress, right? Just because you change does not mean it's good change, but it also means you shouldn't change. You shouldn't not change as well. But this seems to be contradictory, right? I'm telling you, be ready to change, but also be careful to change. But I think that's good advice, right? Don't be so willing just to jump 100% into something because that can bite you, but don't be so like rigid where you're not willing to be flexible and adaptable. So then the next question is, what are the strategies for successfully evolving? And we know this, right? Like this is something that's taught to us by biology. Like the reason why machine learning techniques are so good is that they abide by this concept of survival of the fittest. Well, has anyone learned, just out of curiosity, any kind of like machine learning principles about like genetic algorithms or how you can kind of create a fitness function that you're evaluating to see what your best solution is? Well, you can think of what you're trying to do as a software engineering as defining a fitness function for your possible ways of evolving. And so how do you apply this kind of fitness? Well, it's a measure, right? You got to define a measure, and you do a little bit of testing on this measure to see what works, and then you kind of adopt what works, and you find out what doesn't work, and you kind of get away from that. So the same way, any kind of learning, that's just learning in general, right? But I think there's a power in defining what the learning process is. So survival of the fitness requires a fitness function. So here, that means we got to develop systems and measures. So we compare, if we evolve this way versus this way, which way's better? Or if we stay the same, is that better than evolving at all? And then support the analysis. You got to use these measures to make informed decisions about adopting new technologies or processes, ensuring they contribute to long-term success. Okay, I'm just going to answer this question for you about reflecting on 10x loss. Can you think of an example where you've actually had to deal with that in a technical domain? And we'll just say this was the slide for Workday. Like everyone, like last I heard, like the chair of the department hasn't been able to send like emails out to the student population. That's a big failure at the most like remedial level. This class was actually signed into 2 rooms simultaneously. I had like the Waveco of classes. Yeah, I was in a quantum state. That. Yes. So that brings us to the next subsection of this chapter, the importance of measures in software engineering. So let's talk about what inadequate performance metrics are, right? So common metrics that used to be used to evaluate a software engineer might be like the number of lines of code that they author, or say, for instance, their velocity or test coverage, which can all be misleading, right? These traditional measures often fail to actually accurately measure software quality and productivity. To try to map this into another domain, this would be like trying to evaluate an author's out of a collection of authors, like who the best author is based off of a word count, instead of, say, for instance, the quality of a story. No one's going to say that the book that has like 3,000 pages is going to be the best just because it had that many words. So why traditional metrics can be misleading? Well, lines of code, higher code volume doesn't actually equate to better productivity or code quality, as is, I think, self-evident. I don't even have to justify that any more than the example I gave. It can result in unnecessarily complex code as well, and actually discourage essential refactoring. So sometimes, like, if you reward just producing a large volume of code, that's what you're going to get. And same with test coverage. High coverage rates might appear like you're successfully doing something, but it could actually create a false sense of security. Oh, I passed all the tests, so this is definitely ready to go. So it's not just about the test coverage. So what is it about then? Well, we have to evolve towards a meaningful measurement. So we got to take these traditional views on measurement and look at what we've already said works, agile development. Now, when we talked historically about agile practices, they were actually skeptical about using metrics to measure team performance, favoring flexibility and adaptability, right? Again, we talked about that. We don't want to talk about optimality. We want to talk about adaptability. But we still need a way to measure. So how do we measure with that in mind? And so you have what's called the Accelerate model, which was developed by Nicole Bergström, Jez Humble, and Gene Kim, where they focus on using empirical data to establish meaningful metrics. And there's going to be two meaningful metrics we're going to define. One that's called stability, which measures your reliability, and one that measures your throughput, which assesses your efficiency. These are the two things we really care about in this more agile environment. So let's talk a little bit about what stability means. Here, we're going to talk about change in fail rate. So the frequency of defects from changes, how stable is your code space, the recovery time, so the speed of recovery from failures, and significance, which reflects the software reliability and quality. So we can break down our stability in these three kind of categories. And then our throughput, we can talk about in terms of lead time, which is the duration from idea to deployment. Deployment frequency, which is the rate of successful deployments between each cycle. And the significance, which indicates the development efficiency and speed, and how significant that deployment is, right? It's like just adding comments might not be a very significant deployment. Okay, so let's talk about how we can transform decision-making with the Accelerate model. Because remember, the idea of having a measure is that it allows us to compare one thing to another. The reason why we want to build a measuring system is so that we can use it for our decision-making. So here it gives us predictive capabilities. We can then use stability and throughput metrics to forecast future performance, to get an idea of how quickly the team is developing a code base, so we can make realistic concepts of how long it's going to take to complete the project, whether we're going to have to delay or how we can assign the task out. It also helps teams pinpoint areas for improvement. High-performing teams. So let's now talk about what it means to have a high-performing team based off of these measures versus a low-performing team. A high-performing team is one that will achieve high stability and throughput for superior software development. Usually they can use test automation, trunk-based development, or deployment automation and continuous delivery to achieve that, right? That's what's gonna increase your measurable stats there. So a low-performing team would actually, well, very predictably be on the other side of that scale where they would lack the automation or the complex branching strategies or they might do manual deployment or infrequent releases. So these are kind of the things, kind of the behaviors you could see in a team that you would measure and then assess how agile are they. So we can now start defining a measure of agility. Okay. Let me see. I kind of want to make sure I get through the core portions of this before we run out. I have about 5 minutes left. So the next part would be just talking about applying stability and throughput. So we talked about these as measures. So how do we actually apply these as software engineers? So if our stability is the measure of quality and reliability of our software, by tracking metrics such as our change failure rate and recovery time, and if our throughput evaluates our efficiency and productivity through measures like our lead time and our deployment frequencies, then we can use these for a data-driven framework to be able to develop a culture, a selection of technology, and a selection of our software development tools that facilitate that. And you can kind of identify so if those are our 3 pillars, at any point, if there's a lag, if there's a slowdown, if you notice that there's a measurable difference between one pod and the others, you can try to isolate which of those 3 pillars it is that's causing them. And so here, this brings us to a case study where there was an attempt to actually use these measurements in an environment. It's called the Change Approval Board in software development. I'll just cut to the story and said, this is clearly a failure. This is an example of you're trying to do agile, and there's a reason why your agile practitioners are like, we don't want to have to measure, because then once you start measuring, you get a rigidity that creates a kind of breakdown in that process. But there was this realization we can measure these things. And there was the attempt to actually go ahead and create like a influential body that can then have to cause the cycles to run through this kind of governing system, and it didn't work. It actually did the opposite of work. It actually made things worse. And so it doesn't mean that that failure was meaningless. We learned things from that failure. And so moving forward, what we do is we apply these measures across development for adopting our new technologies within the team itself, not from an external board, for process improvements and for cultural changes. So again, it has the idea is that these things work because it's organic. It's coming inward and not thrusted outward. So the practical examples of using these methods for decision making for you as software engineers working alongside your team members is you want to use continuous delivery, you want to use trunk-based development, and you want to use deployment automation. We've already kind of mentioned that. If you need hardened definitions, I provided on this slide here. But I think it's very obvious when we talk about trunk-based development, there's a reason why we're using version control and Git. That's what that provides for us. When we're talking about continuous delivery, we're talking about why we use a repository, a remote repository that you can synchronize with. And when you're talking about your deployment automation, again, these are all the tools that we're going to be learning about in the next couple of weeks. And I'll say that there is a trade-off. So if you do attempt to, say, for instance, improve stability, it might be at the cost of throughput. Stability might come from additional testing. Additional testing might prevent you from having more throughput in terms of deliverability on your teams. So understand there's no silver bullet, right? And if you try to improve one, it could be at the cost of the other, and that's fine. You have to make a decision of what's right for your team and what's right for the project. Okay. Okay, so foundations of software engineering discipline, our core competencies. We've talked about this before. You want to embrace your creative discipline. You want to focus on learning. You want to make sure that your software has a long-term relevance. We've hammered this point again and again and again. How can we guarantee that? Where there's the 5 core behaviors for effective learning. That's working iteratively. That's employing fast, high-quality feedback. That's working incrementally, that's being experimental, and that's being empirical. Have we not already talked about this in a prior lecture? Or am I imagining it? I feel like I've talked about these concepts before. Well, and of course, we've already compared agile principles to those that don't work, like, say, for instance, the waterfall model. And then let's see here. And so the last thing that I kind of want to mention before I kind of close out on chapter 3 that really brings these concepts together is that when we think about software engineering, we should think of it in 2 different lights. First of all, we should think of the inherent complexity in building code, but also the inherent complexity of having institutions or organizational structures of people. So if we think of the inherent complexity to software development, that involves multiple interconnected components, which you have to find a way to work together. And so your challenges here are concurrency and coupling. Those are the 2 challenges we've identified, and you're going to definitely see that when you actually start working on a project, or on projects, I should say in plural. But then let's transition that to this idea of organizational complexity. Just as a software system faces complexity of interconnected components, our organization also has this intricate system that relies on itself. And so actually we have then what's called Conway's Law. And so Conway's Law is any organization that designs a system, defined broadly, will produce a design whose structure is a copy of the organization's communication structure. That's why it's so important to have a strong communication structure in your team. It's going to be reflected in the way that you get your actual software components and packages and whatnot to work together. So if everyone is like building spaghetti code, that's like all like in one main function, because that's just the way they operate, that's going to be an awful product. And it's a breakdown at the very top level. So if you have better organizational practices in the way you communicate, that will actually start to reflect in your organizational practices in your code base. It's not a rule, it's a guide, but it's a guide that has stood for since 1967. And again, the reason why you want to manage complexity, and again, this is part 3 of the book, is otherwise you get things like big bowl of mud systems. You get technical debt, you get high bug counts, and you get a change to an aversion to change, where it's so difficult to work on the project, you dread having to update. And that's why we need thoughtful design. And again, our core principles for managing our complexity. So we said part 2 was learning. That's what I just showed you a slide before, which we'll go into greater detail later on. But the third part of this course will be managing the complexity. And here we'll lean into modularity, cohesion, separation of concern, information hiding, and abstraction and coupling, which we've mentioned already. But we'll have entire part of the book that dedicates on that and on learning, effective learning. And between those 3 parts, they should bring you together so that you can become holistically a much stronger developer. You can become a software engineer. And that's what the goal is. Excellent. And that is chapter 3. So we're done part 1 of the textbook. I'll probably go ahead, and my goal is to do a workshop for you on Python on Thursday. And then I would love to roll into the workshops moving into next week. I already have the first week planned out. We're going to start with IDE, the IDE workshop, and then on that Thursday after, we'll do the API design workshop. Any questions before I let everyone go? Okay, I will go ahead and post these slides, and then what I'll do is I'll go ahead and post all the videos up till today.
Like,